Hodgkin-Huxley model by Jessica Jahal. The Hodgkin-Huxley model is a set of 4 ordinary differential equations which simulate action potentials, which is neurons firing. So the fundamental unit of communication in the brain is the action potential, which is a temporary polarization of the neuron, which gives it an electrical charge. And so this is how neurons communicate from one to the other by passing this electrical charge. Neurons are polarized by the flow of sodium and potassium ions through gates in the cell membrane, as you can see here. For a channel to be permeable, each one of its gates must be open, and the probability of a gate being opened is determined by the voltage of the membrane, and this also tells you the proportion of gates that will be open. And the variables of voltage, time, and the conductivity of the membrane can all be linked to simulate action potentials of neurons. I chose this model because I'm interested in applying mathematical models to biochemistry and medicine, and particularly the nervous system, because I think it's really interesting how this model gets us closer to understanding the link between human sensation and perception. The Hodgkin-Huxley model was developed by the biophysicists Sir Alan Hodgkin and Sir Andrew Huxley in the mid-20th century, and they were awarded the Nobel Prize for their achievements. Before this model, the existing hypothesis was that during an action potential, the cell membrane basically breaks down completely and allows everything to pass through it. And so during rest, the membrane potential is negative 70 millivolts, around there. And so they hypothesized that during the action potential, it would become 0 because there's no difference between the external environment and the cell itself. However, experiments by Hodgkin showed that there was actually a period where the difference became positive. And so this indicated that there was selective permeability. Not everything was being let through because there was a difference between the outside and the cell. And this peak in charge is known as the absolute refractory period. Hodgkin and Huxley then used the squid giant axon in their experiments to manipulate ionic concentrations and then develop their mathematical model. And the squid giant axon was ideal for this study because of its large diameter, and the data they collected was then used to form the model. So first, let's take a look at how the flow of ions changes over time during an action potential. The membrane potential begins polarized, which is negative at rest, and is depolarized as sodium channels and open and allow the sodium ions to flow inside. So this is why it increases in charge. And then repolarization, bringing it back down to the negative, occurs when the potassium ions flow outside of the cell, making its charge lower. And there's also a temporary period of hyperpolarization where it actually gets negative below baseline, but it eventually returns to its resting value. So each sodium channel has 3 activation gates, which are called the M gates, and 1 inactivation gate, which is the H gate. Every gate must be open for the channel to be open, and ions flow through, for ions to flow through. So the M gates open rapidly in response to depolarization, while the H gate opens slowly in response to polarization. So at rest, the M gates are closed and the H gate is open. When the membrane is depolarized, the M gates will open and the H gate will slowly close. So there's a window of time where the channel is open, and this is how the sodium ions get in. And eventually the channel will shut and it becomes inactivated. And then when the membrane becomes repolarized because of potassium ions, the M gates rapidly shut and the H gate opens. And so this is why we see the sodium conductance go back down. And then the channel returns to its original position. And the potassium channel is a lot simpler. It's just made up of 4 gates that react slower than the sodium M gates, and they're called N gates. If the membrane becomes depolarized due to the flowing in of sodium ions, then the K channel slowly opens, and once the membrane is repolarized, it slowly closes, which is again why there's that hyperpolarization. So alpha and beta are called the transition rate constants, and they represent the number of times per second a closed gate opens and an open gate closes, respectively. So if P is the probability of a gate being open, then we can write the fraction of gates open as A times 1 minus P, and the fraction of gates closed as beta times P. And during equilibrium, these will be equal to each other because the overall number of gates open isn't changing. So we can solve for P here. And then I also know that the rate at which the proportion of gates open is changing is equal to the amount that are opening minus the amount that are closing, because that's how much would be changing. And so if we solve this differential equation using methods we learned in this class, putting it in linear form, and so on, we get back to this P equals alpha over alpha plus beta, showing that it's valid. And then if we plug in the M, H, and N for each of the different type of gates into P to represent the probability of each of those gates being open, we get the first three equations of the Hodgkin-Huxley model. So moving on, for a K channel, the probability of it being open is n to the fourth, since it has 4 n gates. The conductance of K is therefore the probability of it being open times its maximum conductance. And the same can be said for sodium here. And then the conductance times the difference between the membrane potential and the equilibrium potential gives us current, which is I. And so there's also the potassium current, sodium current, and there's also a leak current, which is basically like a constant leak because it's not a completely airtight system. And here's a visualization of that circuit. And then finally, the capacity current, which is this right here, is equal to the ionic current plus any external current that there might be. And if we, this here is negative because of the way that the ions are flowing and just the way it's been standardized. And then if we solve for the dV dt, the membrane potential with respect to time, then we get this whole equation. So what does this all mean? We have the external current influencing the membrane potential, influencing the gates, influencing the channels, then impacting the conductance to the current back to the membrane potential. So this very complex system of equations brings us back to the action potential. That's what we're modeling. So how would we solve this? It's very difficult to get an actual solution since there are so many equations and variables, but we can use a variety of different methods to get very good approximations. So there's the forward-Euler method, which can be used to solve a dE with a given starting point. The slope at that point will be used to create a tangent line, and then we evaluate the tangent line a small step over to find the new point, and then continue on from there to create a curve. There is also a more accurate and more painstaking method called the Runge-Kutta, and what this does is it takes weighted averages over multiple increments to locally linearize the solution. So as you can see, this is going to be a lot more accurate because we're taking weighted averages and multiple increments. And then here we have the actual action potential compared to a variety of different estimations. And as you can see, for all purposes, it's pretty close. And takeaways. From this project, I learned a lot about how math is never going to be perfect, and since it's trying to model and bring regularity to the inherent chaos of the universe, so the model's never going to be perfect. And before completing this project, I thought that interdisciplinary study meant you're sacrificing complexity to study both subjects at the same time. But I couldn't have been more wrong. After seeing how complicated this model is, interdisciplinary study allows you to understand a concept in multiple dimensions, which is going to deepen your understanding. And finally, moving forward, I'd like to learn how to code, since I saw that this was a large part of solving for DEs and testing different estimation methods. And I think overall coding is a very useful skill, and also has a lot of applications in mathematics. The end. Thank you.